Hello everyone, welcome to Robert Morris University Math 0900, Chapter 5, Lesson 1. This is Brianne Pernick, and in this lesson we are going to learn how to factor polynomials whose terms contain a common factor. Essential for this lesson, you must know the following vocabulary words: factor, two-factor, common factor, and greatest common factor, which is very commonly referred to as GCF. We're going to start by learning what the term factor is and what it means to use it as a verb when we say to factor an expression. Excuse me. Factors are numbers, variables, or algebraic expressions that have been multiplied together to create a final product. When you are asked to factor an expression, and that is your directive, what you're being asked to do is to break that expression apart into the specific factors that have been multiplied together in order to produce that expression in the first place. We're going to start learning to factor expressions by learning how to factor out what's called common factors. We can think of this process like dividing out what is common between each term, or we can think about it as in using the distributive property in reverse. So we're going to start by identifying the greatest common factor of every single term. You want to think to yourself, what can I divide out of every single term in my expression? And the strategy that I'm going to teach you to do this is one that I like very much, and I call it upside down division. So let me show you how this works. As we look at example A, the first step is to identify the GCF between the two terms that we have here. We have 3x and we have negative 6y. Those are our two terms. So we're going to start by identifying the GCF. So you want to ask to yourself, what am I going to be able to divide out of both of those terms? What do they have in common that I'm going to be able to remove? Both of them are divisible by 3. So that is going to be the GCF that we're going to start with. Now, we are going to use, as I mentioned, what I call upside down division. So once you identify your GCF, you're going to go ahead and write it on the outside of an upside down division bracket. And then you're going to write your expression inside that upside down division bracket. So now you want to think to yourself, 3x divided by 3 would leave me with what? Well, it leaves me with x. Negative 6y divided by 3 would leave me with what? Well, it would leave me with negative 2y. Once you complete that upside down division, you look at the expression that you just created and check to see if there are any further factors, or GCFs, that you can remove from that expression. In our particular example, there are not. So what you do is you take what you have remaining on the bottom, and that's going to be the main expression that gets plopped into the parentheses. So I'm going to go ahead and write it down here inside parentheses. And the number that we factored out, that GCF, gets written in front of those parentheses. We now have a factored expression. And if you were to use the distributive property and multiply that 3 back in, you would see that we would get right back to where we started with 3x minus 6y. That's how the upside down division method works. So let's go ahead at this point and try example B. I would like for you to try this one on your own. Please pause the recording, and as soon as you're ready to check your work, please press play and we'll check our work together. Okay, by now you should have had an opportunity to work on example B. And the first step for you is to identify the GCF of the terms in this expression. So you want to ask yourself, what can I divide out, or what do the terms have in common? Well, there's nothing that can be divided out of 9 and 2. So now we're going to look at the variables. They both have an x, and that's the only thing that they both have in common. So that means that my GCF is x. So I'm going to write the x in front of the upside down division bracket, and then I'm going to write the 9x plus 2xy inside it. And I'm going to prepare to divide. 9x divided by x will leave me with 9. 2xy divided by x will leave me with 2y. You're going to look at that new expression that you created. Make sure that there are no more common factors. And once you're positive that there are no more common factors, then you know you have your final answer. So what you have left underneath the division bracket gets moved on down into parentheses, and what you have in front is, which was our GCF, gets put in front. So our final answer here is x times the quantity 9 plus 2y. You can check your work using the distributive property, and you will find that we get right back where we started with 9x plus 2xy. We're now going to look at an example that contains 3 terms. And what's special about these terms, as you look across that expression, is you're going to see that the first term has an x to the first power. The second term has an x squared, and the third term has an x cubed. So they all have x's in common, but what you have to determine is how many do they have in common? How many do they share? How many can you remove? So we have to think logically as we do this. Now, as for a beginner that's just learning how to factor expressions, I recommend that you start with your coefficients. And I recommend that you start by identifying the GCF of your numerical coefficients first. So let's look at 24, 12, and 36. What's the GCF of those 3 numbers? What's the largest number that we can divide out? I can divide out a 3 from all of them. I can divide out a 4 from all of them. I can divide out a 6. I can also divide out a 12. It just so happens that 12 is the largest number that we can take out of there. If you don't see that largest common factor right away, it's okay, because I'm going to teach you what to do in the event that you have to do this process a couple of times. So what we're going to do is go ahead and bring that 12 out front, and we're going to set up our upside down division and bring down 24xy plus 12x squared plus 36x cubed. And we're going to get ready to divide. 24xy divided by 12 is going to give us 2xy. 12x squared divided by 12 is going to give us positive x squared. 36x cubed divided by 12 is going to give us 3x cubed. Now, as you're looking at this new expression that we have created, we want to look for more common factors. So let's look at the coefficients. We have a 2, a 1, a 3. Nothing in common there that I can divide out. So I'm going to move on to my variables. So as I've mentioned, I have 1x in my first term, 2 x's in my second term, and 3 x's in my third term. So they all have an x in common. So you want to think to yourself, well, they all have x's. What's the largest number of x's that I can take? This one only has 1x. This one has 2 x's, and this one has 3 x's. You can only take what you have. So since our first term only has 1x, we can only remove an x to the first power. You can't take what you don't have. So now we're getting ready to divide out that x. So 2xy divided by x is 2y. X squared divided by x is 1x. Think logically about that. If you had 2 and you took 1, you should have 1. Okay? And now we have 3x cubed divided by x. And that's going to leave us with 3x squared. Let's think logically again. If we had 3 and we took one of them out, we should have 2 left. So now we're going to look one more time at the expression that we've created and make sure that we don't have any other common factors left. I have 2y, x, and 3x squared. The first term does not have any x's, so I can't use an x. The other two terms don't have a y, so I can't take out a y. And we already established that there's nothing that I could factor out of a 2, a 1, and a 3. So that means that this expression that I have underneath my upside down division bar is the final main expression there. So we're going to go ahead and put that inside the parentheses. And what you factored out on your left-hand side has to get multiplied together. So back to this statement here. If you didn't notice that 12 was your largest GCF, maybe you started with 4, and then you would have had to factor out a 3 in your next step. That's okay, because the final step here is that we have to multiply all of these individual common factors together to get the final GCF of this entire problem. So that means that the whole GCF, for example 2, was 12x. And the final answer for example 2 is 12x times the quantity of 2y plus x plus 3x squared. Now let's go ahead and take a look at example 3. There are 2 parts to example 3. There's an A and a B. I'd like you to go ahead and try part A right now. Please pause the recording, try part A, and as soon as you're ready, we will check your work together. Okay, at this point you should have had an opportunity to do part A. So the first thing that I suggest that you look for is the GCF of your coefficients. So as you're looking for that, you want the largest number that you can divide out of your 12 and you're 18, and you should have found that to be 6. So we're going to put 6 in front of the upside down division bracket, and then we're going to rewrite 12x squared minus 18y squared. And now we're going to prepare for division. 12x squared divided by 6 leaves us with 2x squared. Negative 18y squared divided by 6 leaves us with negative 3y squared. At this point, we're going to go ahead and look at the new expression we created to see if there's anything in common that we can remove. 2 and negative 3 do not have any further common factors. The first term only has an x, and the second term only has a y. That means that there's nothing more that I can factor out. So we have 6 times the quantity 2x squared minus 3y squared. And that is our final answer. Letter B, very similar. We're going to work on exactly the same concept. You want to look across those terms and determine what they have in common that you can remove. I suggest that you work one variable at a time. Please go ahead and pause the recording, and as soon as you're ready, press play and we'll check your work together. Okay, at this point, you should be ready to check the work for example B. As you look across the terms, and we start with the x variable, the first term has 2 x's, the second term has 1 x, and the third term has no x's. So that means that they do not have an x in common. So now we'll look at the y's. The first term has 2 y's. The second term has 2 y's, and the third term has 3 y's. Let's put that back where it belongs there. Okay, so as we're looking at that, and we've determined the number of y's that each term has, you want to decide on the maximum number of y's that you can factor out. That's the next step there. So you're going to focus on the largest number that each contains. If you have 2, you can take 2. But if you don't have 3, you can't take 3. So in other words, you're going to focus on the smallest number of y's that you have, which is 2. So we're going to take out y squared from our expression. So we have x squared y squared plus 3xy squared plus y cubed. And start that upside down division process. X squared y squared divided by y squared leaves us with x squared. 3xy squared divided by y squared leaves us with 3x. Y cubed divided by y squared leaves us with just 1y. Think logically about what we did here. We had 2 y's. We took 2 y's. We have no y's. We had 2 y's. We took 2 y's. We have no y's in the second term. And in the last term, we had 3 y's. We took 2 of them away, and we have 1 left. Okay? You're going to look across that expression one more time just to make sure that you've removed out all of the common factors. We have. So that means our final answer is y squared times the quantity of x squared plus 3x plus y. We can solve example 4 the same way. Remember, I do recommend that you start with your numerical coefficients and then move on to a variable and then move on to another variable if necessary. Please go ahead and pause the recording, and as soon as you're ready, we'll go ahead and check your answer. Okay, at this point you should be ready to check your answer for number 4. As you are looking across your expression, you should have seen that an 8 can be factored out of every single one of those coefficients. So we're going to start by factoring out an 8. So we're going to rewrite our expression 8x cubed y plus 16x squared y squared minus 24 x cubed y cubed, and start the upside down dividing. 8 divided by 8 is going to leave us with a coefficient of 1, so I'm going to bring down my x cubed y. 16 divided by 8 is going to leave me with a coefficient of 2, so I'm going to write 2x squared y squared. Negative 24 divided by 8 is going to leave me with a coefficient of negative 3, and bring down my x cubed y cubed. Next, I want to check my variables. As I look across my problem, I'll see that I have 3 x's in my first term, 2 x's in my second term, and 3 x's in my third term. So they all contain an x. So now I just need to decide what's the highest power of x's that I can remove. I have 3, 2, and then 3 again. So we want to focus on that smallest power, which is 2, because remember, we can't take what we don't have. The middle term doesn't have 3, so I can't take 3. I can only take 2 out of each term. So x cubed y divided by x squared leaves me with xy. 2x squared y squared divided by x squared will leave us with 2y squared. Negative 3x cubed y cubed will leave us with negative 3x y cubed. We're going to look at our expression one more time. We want to see if there are any other common factors that can be removed. So let's focus on the y's at this time. Our first term has 1y. Our second term has 2. Our third term has 3. That means we will be able to remove 1y. So we'll start the division process. xy, divide by y, leaves us with x. 2y squared, divide by y, leaves us with 2y. And negative 3xy cubed, divided by y, leaves us with 3xy squared. At this point, you want to check your expression one last time, just to make sure that you have taken out every single common factor that you can. We have. So we are going to bring that expression down into parentheses. And remember, every common factor that we took out on the left will get multiplied together to form the GCF of the expression. So we're going to take 8 times x squared times y to get 8x squared y, which we plop right there in front of our set of parentheses. If we were to multiply those all back together using the distributive property, we would get right back where we started. Example 5 is very similar. Please go ahead and try this one. Please pause the recording, and as soon as you're ready to move forward, press play and we'll check our work together. Okay, at this point you should be ready to check your work with me. As you look at your two expressions, you should have seen that you can divide out a 9, and that is the GCF of your coefficients. So we're going to have 9a cubed b squared. Oh, let me rewrite this here. My apologies. All right, so we're going to use 9 as the GCF of our coefficients and set up the upside down division. So we're going to rewrite our 9a cubed b squared plus 9a squared b squared. Starting the division process, 9 divided by 9 is 1, so that leaves us with a cubed b squared. And dividing one more time, we're left with a squared b squared. We can now look at our a's. Our first term has 3. Our second term has 2 a's. That means that we can take out 2 a's. So I'm going to factor out an a squared. A cubed b squared divided by a squared leaves me with a b squared plus a squared b squared divided by a squared leaves me with just b squared. One more step here. We can divide out a factor of some type of b. Both terms have a b squared. That means I can take out a b squared. So ab squared divided by b squared leaves me with a, and b squared divided by b squared leaves me with 1. Remember, when you're subtracting those exponents and you get an exponent of 0, 2 minus 2 makes 0, that makes a 1. Okay, b squared over b squared cancels into a 1. At this point, we have nothing more that we can factor out, so that means that that's our final expression there that will be put into our parentheses. And everything that we removed on the left-hand side has to get multiplied back together to form the GCF of the expression. So 9 times a squared times b squared. So we have 9a squared b squared times the quantity a plus 1. Now, example 6 is slightly different. This is going to introduce us to the concept called factoring by grouping. And it's essentially the same thing of what we've been doing. However, you're going to notice that you have a group that is exactly the same. When that happens, if you look at your groups, we have x minus 4y and x minus 4y. Those groups are identical. And since they are identical, we can use that identical group as a GCF, so to speak. So what we're going to do is drop it down into our next line, that whole group. Since it's a common factor, both terms have that group. The group is identical, and it's a common factor of both terms. We can use it as a GCF. So we're going to go ahead and drop it down into the next line. Now, the two things that we have left remaining in that group, which are the 3x and the positive 2, those are going to simply get written in the last group right there. And that's our final answer. We have x minus 4y as the first group and 3x plus 2 as the last group. You don't need to do any further work for that one. Example 7 is very similar. I'd like you to try this one, and I'm going to give you a little hint here that this is a -1 in front of that parenthesis. That should help you out as you're doing this one. So please pause the recording as soon as you're ready. Please continue on, and we will do the problem together to check your work. Okay, by now you guys should have completed example 7, and you should be ready to go over the answer with me. So the first thing that you should have noted is that you have a common group. So this means that we can use factoring by grouping. So what we do whenever we have a common group, which is 2x minus 3y, is we're going to go ahead and drop that entire group down into our new line and make a new group for the factors that are remaining, which were 7x squared and -1. So we bring those two terms down into the new group of 7x squared minus 1. And this here is our final answer. Example 8 is a real-world problem that helps us to utilize factoring, or shows us an application of how it can be useful to us, I should say. Excuse me. It says that a computer programmer is writing a program to find the total area of 4 circles. She uses the formula A equals pi r squared. The radii of the circles are A, B, C, and D, respectively. She wants the final answer to be in factored form with the value of pi occurring only once in order to minimize the rounding error. Write the total area of the 4 circles with the formula that has pi occurring only once. This second to last line here, where it says that the computer programmer wants to minimize the rounding error, is very important. If you think about how we find area of a circle using pi r squared, if we had to calculate all 4 areas individually and then add them back together, that means that we would have rounded 4 times, which gives us room for error 4 times. If we set this problem up the way that the programmer wants us to, and we only have to use pi 1 time during our end result, then that means that we would only have to round 1 time and only have error incorporated into our problem 1 time. So let's think about what's going to happen here. We're going to have the area of 4 circles being combined together. So we have pi r squared plus pi r squared plus pi r squared plus pi r squared. Okay, that's going to represent the 4 circles area and how I have to total them together to get the total area. I'm going to put a little t here so that we know that that represents the total area. Now they did tell me that each circle had a different radius. So my first circle had a radius of A, so I'm just going to make those substitutions. My second circle had a radius of B. My third circle had a radius of C. And the last circle had a radius of D. So nothing has changed except I've made those substitutions. Now, looking across this expression, you should see that every single term has a factor of pi. we can use what we learned about factoring out the GCF to remove that factor of pi and only leave the radii squared in our expression. So if I pull that factor pi out front of my parenthesis, think about what happens during that upside down division. Okay, pi a squared divided by pi leaves me with a squared. Pi b squared divided by pi leaves me with b squared. And so on. When I factor out that pi, we're left with pi times a squared plus b squared plus c squared plus d squared. If you distributed it back in, you would get back to where we started. But this final formula has pi written just one time, and it's going to allow us to square the radii, add them together, and then multiply by pi, thus only having to round one time. Okay. I would like for you to do student practice 8. Please go ahead and read the problem, think about what's going on here, and how we can solve this problem. It's going to be pretty similar to what we just did. As soon as you're ready to move forward, please press play and we'll review the answer together. Okay, by now you should have had an opportunity to complete student practice 8. This problem says that we're going to use the area formula for a circle to find just the shaded region. The radius of the larger circle is b, and the radius of the smaller circle is a. Write the shaded area formula in factored form so that pi only appears once. Now if you think logically about what's happening here, the pink circle is part of a whole circle that's just being covered by this grayed out circle, if you think of it that way. You can find the area of that whole pink circle and then subtract out the part that's grayed out to remove it. Kind of like a donut, if you think about that. Find the area of the whole donut and then find the area of just the hole in the donut. Think about that for a minute. I refer to these problems, it's a pretty generic explanation, but it's always helped my students remember them as big minus small problems. When you have a shaded type of problem like this, you're going to have some type of big figure and you're going to have some type of smaller figure on the inside that is impeding your ability to find the area of that big thing. So what we do is we focus on finding the area of the whole big object, and then we subtract out the area of the small object, and that's going to leave us with just the portion that's remaining. And I call that a big minus small problem. Not very technical, but it helps us to remember the process. So let's focus on what we're doing here. If we want to find the area of just the shaded region, we're going to start with the area of the whole circle. So we're going to do pi r squared for the whole circle, and then subtract out the area for the gray circle. So another pi r squared. So for the whole circle, which starting at the center and going out to the edge, its radius was b. So that we'll plug that in. We have pi b squared minus the radius of just that gray circle is a. So that's pi a squared. Now the problem said that they only wanted to have pi written one time. If you look at your expression, you can see that both of those expressions contain pi, so we can factor it out. When we factor it out, we're left with b squared minus a squared inside our parentheses. And there's our final answer for this problem. For this section, I'll leave you with just some directions on how to factor a polynomial with common factors. So you can keep this for your reference and read through it as you need to. And as always, if you had trouble with this section, please feel free to contact me and ask questions as needed. Thank you.